Hello students. So we're moving on to our next topic, gravity, but we're going to look at it in more detail, and in particular like the gravity between planets, the sun and planets, the moon and the earth, and so on. Now, we have this symbol little g, which we give the value 9.8, or more exactly 9.81 meters per second squared. And that's the rate at which an object will accelerate due to Earth's gravity. It also gets used this way, where if I have a 1 kilogram, the weight of that 1 kilogram will be g times the mass, the 1 kilogram, and that gives us 9.8 newtons. So anyway, you're familiar with that. Now, you might be aware that this number for g is only good at sea level. When you get further away, when you go up high, the value of g changes. It becomes less, actually. So let's look at Newton's law of universal gravitation. So the weight of an object is going to be given by this formula here that Newton came up with. Here's the mass. The little m here is the mass of whatever it is we're measuring. It could be the 1 kilogram. This capital M represents the mass of the Earth, so it's a huge number. The little r represents the distance from our mass down to the middle of the Earth, the center of the Earth. So that's a few thousand miles. And then this capital G is a constant called the universal gravitation constant. So anyhow, you have this nice formula, and it'll tell you the weight of an object at any distance from the Earth. So it works even if you're way up out in space. Almost the same formula, except now you've removed the test mass. This formula here tells you the acceleration. So if you have an object and you just drop it, this is how much it will accelerate. Okay, now let's look at G, the universal gravitation constant. This number is tiny, 6.67 times 10 to the negative 11. Now, the units they look a little strange. Newton meters squared per kilogram squared. The reason why they look like that is that here's where it gets used, right? You've got kilograms and kilograms here, right? But what we want to end up with is newtons, right? So here's the newtons, and then you're dividing by kilograms squared to get rid of the kilograms here and the kilograms there. And then here you've got meters squared, and you want to get rid of that as well. And so that's why you've got meters squared here. Okay. Well, now I want to take a slight detour and talk about scientific notation, because with gravitation, we're going to be doing calculations that involve extremely small numbers, such as the universal gravitation constant, which if you wrote it out in decimal form would look like this, with many, many zeros after the decimal. You're going to do things involving the mass of the sun, which is a huge number like this. So, there's no way that you're going to do this math without using scientific notation. So I'm going to do a brief review here. The notes, I've uploaded these notes to Canvas, so they're there, and you can study this on your own. I think you already know this material. It's just telling you how to construct scientific notation numbers. Here are some examples of turning large numbers into scientific notation. Here's some example. Here's an example for turning a small number into scientific notation. Here are some examples with maybe a little bit of trickiness thrown in. Sometimes people wonder, well, what do I do about negative signs? So that's what these examples are about. And here's the meat of what I want to talk about. I want you to be good at entering scientific notation numbers into computers, such as putting the answers into expert TA problems, which are on a computer, and also how to put scientific notation numbers into calculators like this, right? So let's say we had this number here, 3.5 times 10 to the negative 23, and we wanted to put that into a calculator. What you would type is 3.5 capital E negative 23. Now I said capital E, but more recently computers seem to ignore whether it's uppercase or lowercase. So, but anyway, capital E should always work. E stands for exponent. So the negative 23 is the exponent of the 10. So in other words, it's the power of 10. So that's how you put a floating point, a scientific notation number into a computer. Now, for calculators, it's very similar, but slightly different. You're going to type in 3.5. Then on this particular calculator, to activate this exponent key, which is labeled EE in blue over the reciprocal key. Before that works, you have to first press the second. So if you press the second button, everything that's in blue is activated. So for putting scientific notation, for this number, let's say, I would press 3.5 second EE, or here, and then the next step is I want to put in negative 23. So it's not going to be the minus. No, it's going to be the negative sign key down here. Okay, and then the 23. So you need to, when you do scientific notation on calculators, you need to do it this way. Now this applies to the TI line of calculators. I really like Casio calculators as well. Their keyboard's slightly different. Instead of saying EE, theirs is going to say EXP, and the rest of it's the same. Yeah. Now, the reason why I'm emphasizing this is because there's a very common mistake that my students have made in the past, and I don't want that to happen to you. So the mistake is to do it like this, to put in 3.5 and then the times button, the multiplication button, and then punching in 10, and then the raise to the power button, and then the negative 23. This will get you the right answer 75% of the time, but 25% of the time it'll get you the wrong answer. And so it is a very pernicious thing. People get into the habit because, oh, it seems to be working, let's just do that. But it'll bite you in the middle of an exam or a quiz, and so don't do it. Get into the habit of putting in numbers into your calculator the right way, which is this way. All right. Now here's a challenge. If you're doing it the wrong way, you're going to get the wrong numbers here. So try this out on your calculator. 7.8 divided by 2.6 times 10 to the 44. and so on. So try to do these, write down your answers. You might want to pause the video now because I'm going to show the answers next. All right, I'm showing the answers. Okay. Are these the answers you got? I hope so. Otherwise, figure out what you're doing wrong because this is going to mess you up later on. Okay. The history of the discovery of universal gravitation is really fascinating, and I'm not really going into it. But if you read the textbook, and if you get onto Google and look up the lives of Galileo and Tycho and Kepler and Newton, it's a fascinating story. The way I'm presenting stuff to you, I'm just being practical. I'm just showing you what you need to know to do okay in the class. Now, one thing though that I do want to talk about, it's interesting history, and also you need it for the class, is what I call the distribution of mass puzzle. When you use the universal gravitation formula, you want to use the distance from where your test object is to the center of the Earth. In other words, you're using the formula as if all of the mass of the Earth, all of this mass, all of this rock, was all concentrated at a point right at the center of the Earth. Now, Isaac Newton, when he first came up with that formula, intuitively knew that that's the way his formula should work. But he didn't publish that formula for like 20 years. And the reason he held back was because he knew intuitively that it should be at the center of the Earth, but he couldn't prove it. And he wanted that confidence. He wanted a proof. And so he worked on the mathematics of this thing, and in the process invented integral calculus. And so what happens in an integral treatment of this problem, you say, well, this little chunk of the Earth, it has gravitation that's pulling like this, and this chunk of of rock is pulling like this, and stuff over here is pulling like this. And the process of integrating is really a process of adding up a lot of pieces like this. You divide the Earth up into an infinite number of pieces, find the force from each one of those pieces, and the end result is, oh my God, the end result is that the answer is the same as if you assumed that all of the Earth was at the center. So 20 years of work inventing calculus, and now Isaac Newton is confident enough to publish his universal gravitation formula. Now, another interesting aspect of this is what if you're underground? What if you're in a tunnel? In that case, you've got some of the rock that's above you, right? So here you are standing down in the this is you down in this tunnel, and wow, there's some rock up above you. So here, this rock is pulling this way on you, and this rock here is pulling that way on you, and this rock here is pulling this way. So you're going to weigh less when you're underground, and if you can do the calculus, what happens is you get the answer that your weight is going to be as if the mass of Earth, the mass that is at, you see, here's the radial distance from the center to you. You just need to include all of the rock that's at this within this radial distance. So if you from here to here is r, then also from there to there is also r. From here to here is also r, and so you include all of this of the Earth. What you don't include is the stuff that's at a further radius out. Now think about it. What would be your weight if you were right at the center of the Earth? Of course, at the center of the Earth, you'd get incinerated, right? It's extremely hot. But let's say there was like a little bubble where you could live at the center of the Earth. How much would you weigh then? Okay. Now, what I want to do is change gears slightly. I want to take a look at something in the book. Okay, so right now I'm on page 383 of our textbook. I'm looking at example 12-2, and I need you to really understand this example. And so let's take a look at what it's asking. So it says, okay, you're climbing to the top of Mount Everest, so you're really far up, and what will be the acceleration due to gravity at this altitude? In other words, if you're standing at the top of the mountain and you drop a pen, what will be the acceleration? Will it still be 9.81 meters per second squared? And clearly the answer is going to be no. Let's see how they do it. So first of all, they write down the universal gravitational formula, universal gravitation formula, from Isaac Newton, right here. So the force that's pulling down on some test object, could have been that pen I just mentioned, and between the Earth and the object. So here it is. And now what we would do, before, in previous chapters, we would have just said, well, the force on that pen is mg. But now, since we're up at the top of this mountain at a very high height, a height h above sea level, we're going to call it g sub h, just to distinguish it from regular g. So regular g is 9.81, g sub h is whatever it's going to turn out to be at the top of the mountain. Okay, so here is the universal gravitation formula again, right? Here it is. But what they've done is they've put in the distance from the center of the Earth. R sub e is the distance you are from the middle of the Earth when you're at sea level. And okay, so their notation is capital R, okay, that's radius, and then this E, I think, must stand for Earth, right? It's the radius of the Earth. And then here's H, how high the mountain is. So when you add those, you've got your distance from the center of the Earth. Now, that's the downward pull of the Earth on your test object, and that's the same as mg sub h. Right, so they've got them equated right here. So they've equated these two things. Notice that the little m's cancel, and you've got essentially the answer right here. And now they start plugging in numbers, and you get the answer, which is 9.78 meters per second squared. So I need you to understand this process. This is a good first problem for you to figure out. Having said that, there is, in my opinion, a flaw with this. I think that if you were to actually take a gravitation measuring device to the top of Mount Everest, I don't think you're going to get this number. think about it for a second. What do you think is wrong with what they've done? I mean, it's not really wrong. I mean, this is still a perfectly fine example, but there are some other factors that I think they're ignoring. What I think they're ignoring is the fact that you've got all this extra rock here, right? This stuff here, this rock, it has mass of its own. So if you're standing up here, right, this is you standing on top of Mount Everest, you're being pulled down by the Earth, right? So here is the Earth, right? This is the Earth. It's pulling you down, but you're also being pulled down by the mountain itself. So that would tend to make the 9.78 be an answer that's too small. I have a feeling it might be a little bit bigger than that. But I was researching this, and then another book pointed out another effect, which I hadn't thought of, but it's really interesting. The mountain being very heavy, it pushes down on the mantle of the Earth. So under the Earth, there is the mantle, which is a different kind of rock. It's much more dense. And what's interesting is that the rock goes kind of like this. So it's as if you had like an iceberg. So think of Mount Everest as a sort of iceberg, which is floating on top of the mantle. So you're going to have, here's this mantle material, but which is more dense than regular rock. So you're going to have here a region of less dense rock. So that would tend to make this number be smaller. So we actually have two effects. The mountain, which would tend to make the answer be bigger, and the less dense rock, which is here, which would tend to make the answer be smaller, and I don't know which one wins. But to me, it's interesting that even a simple problem like this has some nuances, which get kind of interesting, in my opinion. Okay, so let's continue. Let's take a look at the history of capital G, the universal gravitation constant. The experiment that measured this number was carried out by Henry Cavendish, and it's one of the most famous experiments in the history of science. It was made even more famous by the New York Times putting a big headline on the front page saying that Henry Cavendish was the man who had weighed the Earth, which is kind of true because once capital G was determined, it was not then possible to determine exactly what is the mass of the Earth. So until capital G of the universal gravitation constant had been determined, people could estimate, but they didn't really know how massive the Earth was. The experiment itself was done by finding the gravitational pull between two lead balls. So here's lead ball number 1, and here is lead ball number 2, and finding the gravitational pull between them. Now, this was a very delicate experiment, and I'm going to stop at this point and show you a little bit about how an experiment like that looks. So here's a picture of the Cavendish experiment redone for the purposes of showing students, in this case at Harvard. Now, I said that there were 2 lead balls, but in fact, there are 4. You can see that there's a large lead ball here and a small one, a large lead ball here and a small one. The large lead balls are stationary, and the small ones are hanging by a thread, which is coming down this tube here, this thread, and then there's like a stick here, and then there's a lead ball and a lead ball. So the 2 small balls can rotate like this. And the thread is actually a steel thread, and it acts as a very weak spring. So when there's no force at all from gravity, except from the downward pull of the Earth, the two small lead balls will have some natural position. Then when you bring the large lead balls nearby, close to them, then the two small ones will start to be attracted, and there'll be a slight bending of the steel thread. I think there is a top view which makes it easier to figure out. Yeah, so here is a top view diagram. The two balls are going to be like this. This is their natural position. And then when you bring the big lead balls nearby, then there's a gravitational pull this way, like this, right? They're being pulled together. By the same token, these two are being pulled together, and so they now they find a new orientation. It's a tiny, tiny motion, and to make the motion more obvious, Cavendish sent a beam of light this way. So Cavendish sent a beam of light to a mirror, and which turned with the stick here, and so the beam of light would move, and so that's how he could see the motion. Here they're saying laser light. Laser light is really nice and collimated, but Cavendish had some regular light, I guess we would call it. Anyhow, that is how the experiment was done. Here I go through the arithmetic, the math for determining the mass of the Earth, now that we know what G is. And there are two things now that I want to caution you about before I finish up. The R between the two objects, be careful. It's the center to center distance. So if this is the Earth, let's say this was the moon, and this is the Earth. Sometimes there are questions that are deliberately tricky and confusing, and they're going to say something like, "Oh, the altitude of the moon is so many kilometers above us," but we're already on the surface of the Earth, right? So if you're not careful, you're going to leave out this amount of distance and maybe this amount of distance. So don't mess up. If it's not the surface to surface distance that matters, that would be wrong. It's the center to center distance. Another thing that I want to caution you about is that in many books, and I think even in our book, the letter R is not always used. The reason why this is called R is because of the phrase radial distance. That's where the R is coming from. But very often, instead of using R, the letter D is going to be used. So just be aware that there's people sort of flip back and forth between using R and using D. And finally, in our book, and I'm going to do this also, there is a tendency to switch back and forth between the names of these two things. So at this point in the book, we seem to be using little m and big M. So like this could be the Earth, which is big, and this could be the moon, which is smaller, or it could be a satellite, which is smaller. Or this could be the sun, which is really big, and then this could be the Earth, which is smaller. Okay, anyhow, that's one approach. But a lot of times it's going to be M1 and M2. And in that case, the universal gravitation formula looks like this. F equals capital G M1 M2 over R squared. Or it could have been D squared. So anyway, just watch out for this changing notation. I'm sorry, but that's just the way it goes. Anyway, thank you for watching.